NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Well, today we're going to talk about one of the great instruments of science, the Voyager spacecraft.
Now entering an enigmatic and uncharted area of space, Voyager 1, which was launched over 40 years ago, is revealing truths that even the most seasoned scientists find unnerving. Built with less sophisticated technology, this ancient spaceship is still traveling billions of kilometers away from Earth. It challenges our understanding of the cosmos by presenting us with discoveries as it goes into the unknown. What bizarre truths lurk in these depths of space? Get ready as we examine the startling discoveries made by Voyager 1, a 45-year odyssey beyond the stars. Just when you think the story would end in quiet, it surprises us with signals that outsmart our advanced technical capabilities. This mission, which was founded in 1977, has broken boundaries rather than merely expanding them. A terrifying revelation that redefines the impossible is about to unfold. Get ready, what is in store for Voyager 1? Keep checking back as we learn more. Something amazing occurred in the field of space exploration back in 1965. Two spacecraft were ready to set out on a journey that would alter the course of history. Gary Flandreau, a gifted engineer at NASA's Jet Propulsion Laboratory, faced a difficult task at the dawn of the space era. He had to determine the most direct route for a spaceship to travel in order to reach Jupiter, Saturn, Uranus, and Neptune, the far-off gas giants. With just a pencil in hand, Flandreau made an important discovery. He understood that all four planets would line up precisely in the sky in the late 1970s and early 1980s, forming a unique cosmic route. Because of this arrangement, a spaceship could travel from Earth to Neptune in just 12 years, as opposed to the customary 30, by utilizing the gravitational pull of each planet. But given that this alignment only occurs once every 176 years, it was a once-in-a-lifetime chance. NASA realized they needed to move quickly. These missions were scheduled in such a way as to maximize this special planetary lineup. Nobody anticipated that these probes would go on to become historical landmarks. Voyager 1 and Voyager 2 are still orbiting the planet more than 40 years later, having traveled further than any other spacecraft. They keep returning insightful data that broadens our understanding of the cosmos and reveals fresh surprises, more than anybody could have predicted. These devices have endured far longer and traveled far farther than expected. They were only meant to work for 4 years at first, but they have worked considerably longer. They have continuously amazed us along the way. Initially, they returned breathtaking images of Jupiter and Saturn's moons, revealing to us that these far-off worlds are considerably livelier and more vibrant than we could have ever anticipated. We witnessed ice fields moving and volcanoes erupting, drastically altering our perception of these distant worlds. Leading the way in this investigation was Voyager 2, which, in 1986, became the first spacecraft to travel near Uranus and, in 1989, swiftly pass Neptune. As the sole spacecraft to have traveled along this route, it has uncovered fresh data from locations more than 14 billion kilometers beyond Earth. The size of an old Volkswagen Beetle, these space probes have exceeded all expectations and continue to deepen our understanding of the cosmos. As the Voyager probe set out to study Mercury, Venus provided them with a gravitational boost, a method never attempted before. They became space exploration pioneers as a result. This was no simple assignment though. There was very little room for error. The outcome could be ascertained in a matter of minutes, and it sometimes required many attempts to get it correct. They had to go through the hazardous asteroid belt on their initial route to Jupiter, which brought them 10 times farther from Earth than Mercury, an issue much discussed in the 1970s. Luckily, Voyager had an easier time navigating this congested area because previous missions like Pioneer 10 and 11 had done so safely. However, Voyager still faced several difficulties. Let's investigate the far-off signals sent by Voyager to uncover mysteries from deep space. Voyager's journey into the unknown required the computers aboard the spacecraft to be shrewd in order to handle all of the chores for their journey, as they had only 69 kilobytes of memory, far less than what your smartphone carries. They used an 8-track tape recorder to retain the data and a transmitter as weak as a refrigerator light to relay it back to Earth. The spacecraft used radio waves traveling at the speed of light for communication, with dish antennas measuring 12 feet in width. However, communication was difficult since Voyager was billions of kilometers distant and expanding every second. For example, it took almost 18 hours for signals from Voyager 2 to arrive at Earth. Furthermore, it became increasingly difficult to distinguish the faint signals coming from the spacecraft due to the growing quantity of signals from Earth, such as those from TVs, radios, and mobile phones. The Voyagers have defied the odds and kept returning with startling new findings from the remote reaches of space in spite of these difficulties. Their research has altered and expanded our knowledge of the vast uncharted regions beyond our solar system. The Oort cloud, a location far away, is made up of ice particles kept in place by the Sun's gravity. The Voyagers are gradually making their way toward this region, which extends nearly halfway to the closest star. Nearer to us, the heliopause, or edge of our solar system, denotes the point where our galaxy narrows and the larger galaxy widens. Estimates of its distance before the Voyager spacecraft arrived varied greatly, but many believed it to be around 50 astronomical units distant, which increased support for the expedition by providing us with close-up views of locations we've never seen before. The Voyager's continued investigation helps us comprehend these far-off parts of space. However, these indicators were absent, which perplexed the experts. In particular, they were searching for a rise in cosmic rays, which are fast-moving, high-energy particles from supernova explosions and other high-energy events. This was not the case. Typically, a rise in these cosmic rays would indicate that the spacecraft had entered interstellar space. Rather, the heliosphere, a massive magnetic barrier that protects the inner solar system from external cosmic threats, was blocking the majority of the lower-energy cosmic rays. As the spacecraft got farther away, the crew keeping watch on Voyager also closely monitored any changes in the magnetic fields. It was anticipated that the charged gases in the interstellar medium, molded by the magnetic fields of neighboring stars, would have a distinct magnetic pattern from that of the heliosphere. However, no modifications were discovered, which further perplexed the investigators. Voyager 1 didn't begin returning intriguing data to Earth until it passed the heliopause, which verified the predicted rise in cosmic rays. This incident demonstrated how unexpected and difficult space travel can be while providing significant new insights into interstellar space. Remarkably, there was no indication of any shift in the magnetic fields surrounding Voyager 2 when traveling from an area of space shaped by the magnetic influence of the Sun to one influenced by other stars. People commonly believed that the magnetic field would change direction. Beginning its journey toward the border of our solar system, sometimes referred to as the interstellar barrier, in November 2018, Voyager 2 arrived at the heliopause situated 120 astronomical units, AU, from Earth. Its duplicate had arrived at the same location 6 years prior. To further complicate matters, Voyager 2's failure to find any variations in the magnetic field defied accepted ideas. Next, we investigate the mysteries that challenge our current understanding near the frontier of our solar system. Examining the limits of the heliosphere, scientists predicted that the heliosphere would contract and expand, like the solar wind, due to the Sun's 11-year activity cycle. Nevertheless, given that the solar wind was very powerful when Voyager 2 landed, none of the existing hypotheses could account for the peculiar findings. Given this intensity, the heliopause ought to have been located more than 120 Australian dollars from Earth. The Voyager probes detected slight variations close to the heliopause, which were brought on by heliosphere-to-heliosphere interactions as they approached interstellar space. However, the magnetic field appeared to be quite steady when viewed across longer distances. This discrepancy gave rise to discussions about whether our existing models were accurate or if the spacecraft would ultimately escape these chaotic areas and locate the genuine interstellar magnetic field. While some scientists believe the Voyagers may still be inside the heliosphere, others argue they have begun to reach interstellar space due to the probe's observations of a substantial rise in galactic cosmic rays and plasma density. Expert debates have been sparked by this new data, tackling one of the major challenges facing space exploration today. It's akin to trying to view an entire room through a fishbowl when attempting to comprehend the heliosphere. To fully understand it, we need a probe capable of observing the solar system from a significant distance. Sadly, despite the obsolescence of technologies like answering machines and VCRs, the Voyager spacecraft continues to operate against all odds. They use software that is primitive by today's standards and rely on technology that is more than 50 years old. Instead of utilizing complex coding, the original developers designed the systems with simplicity in mind. Currently, Voyager 1 has 4 operational instruments, whereas Voyager 2 has 5. These spacecraft are powered by an apparatus that converts heat from the radioactive decay of plutonium into energy. However, NASA must carefully decide which systems to keep running to conserve power, as the spacecraft lose about 4 watts of energy per year. For instance, engineers had to turn off the heater for the cosmic ray detector 3 years ago, even though it is essential for determining when the spacecraft leaves the heliosphere. Remarkably, this detector continued to function despite being exposed to extreme cold beyond its design limits. The magnetometer and plasma science instrument, located within the spacecraft's main body where heat from the computers keeps temperatures higher, are expected to be the last instruments to shut down. In contrast, all other instruments, mounted on a 43-foot fiberglass boom, remain exposed to the harsh elements of space. But the challenges don't end there. If all goes according to plan, the Voyagers might continue operating until 2030. Power is the primary limiting factor. Voyager 1 will pass the nearest star to Earth, Proxima Centauri, in approximately 16,700 years, followed by Voyager 2 around 3,600 years later. Long after the Sun and the heliosphere have vanished, these sturdy spacecraft will continue orbiting the Milky Way for millions of years, potentially sending out one last message that no one may be around to hear. The Voyager tale is a testament to humanity's curiosity and drive to explore. Titan Centaur rockets launched Voyager 1 into space, with its twin, Voyager 2, following 15 days earlier. The primary mission of these spacecraft was to study Jupiter and Saturn, the largest planets in our solar system, along with their moons. However, they accomplished far more than expected. The Voyagers traveled farther from Earth than any other human-made objects, even venturing into interstellar space, a region never before visited by spacecraft. Currently, Voyager 1 and Voyager 2 are nearly 12 billion miles away from Earth and continue to send back data that astonishes scientists. Recently, they have uncovered strange occurrences, adding to their legacy of groundbreaking discoveries. The Voyagers began their journey by investigating the moons of Jupiter and Saturn over 40 years ago, challenging preconceived notions about these celestial bodies. Unlike our moon, these moons turned out to be lively and energetic. Voyager 2 made history in 1986 as the first spacecraft to fly by Uranus and later Neptune, revealing incredible details about these distant planets. NASA has implemented strategies to sustain the Voyagers by conserving energy and shutting down unnecessary components, ensuring their continued exploration until at least 2030. The data returned by these spacecraft has sparked new enthusiasm for space exploration and numerous significant discoveries. The scientific community was already intrigued by the images they returned with from the far-off worlds before they ever made it to the outer planets. The crew at NASA's Jet Propulsion Laboratory was ecstatic to see the first photographs of Jupiter's whirling clouds and the renowned Great Red Spot when Voyager 1 began delivering images of the planet. The great surprise, though, was when they looked at Io, Jupiter's moon. Io, a moon that is marginally larger than Earth, has been discovered to be the solar system's most volcanically active body. Unusual signals from Io were picked up by Voyager 1, and the photos revealed powerful volcanic explosions that were launching debris high into space. One of Io's volcanoes erupted spectacularly, sending plumes across an area almost as big as France and reaching heights higher than Mount Everest. Over 33,000 photographs of Jupiter and its moons have been obtained by the Voyager spacecraft, collectively showcasing both the planet's breathtaking majesty and the moon's varied landscapes. However, the amazing findings made by these two spacecraft were only getting started. Even though Jupiter's rings aren't as brilliant as some others, it was unexpected to realize that it had them nonetheless. Jupiter is now much more intriguing in light of this finding. Another surprising development was the discovery by the Voyager 2 spacecraft that Europa, one of Jupiter's numerous moons, is submerged almost 60 miles below the surface in a thick coating of ice. This led to a reevaluation of previous space theories by scientists and renewed interest in the possibility of life on icy moons like Europa. Utilizing Jupiter's gravity to accelerate the Voyager spacecraft was a vital maneuver that enabled them to move away from the Sun and toward Saturn. Voyager 1 approached Titan, the moon of Saturn, which is encircled by a dense orange cloud. This prompted a closer examination of Titan's intricate atmosphere. Following this interaction, Voyager 1 departed our solar system. As all of this was going on, Voyager 2 continued its amazing investigation. In 1986, it passed by Uranus and discovered 11 new moons. When it arrived at Neptune 3 years later, it unveiled the dynamic and intriguing features of this far-off ice giant, including the recording of the fastest winds yet seen in our solar system, winds that might approach 1,000 miles per hour. Voyager 2's approach to Neptune, which was reached in just 2,980 miles, provided startling new information about this distant planet. Triton, the biggest moon of Neptune, with temperatures as low as -391 degrees Fahrenheit, making it one of the coldest locations in our solar system. In addition, Triton featured active ice volcanoes that erupted into a thin atmosphere, spewing icy particles and nitrogen gas. These findings brought to light the variety and allure of the planets inside our solar system, including those closest to it. Notable scientist Carl Sagan was a major force behind the advancement of this space project. His contribution to the Voyager project was significant, and he was particularly keen to get a last batch of pictures of our solar system as a farewell present to the human race. When Voyager 1 rotated its camera back towards the inner solar system on Valentine's Day in 1990 and captured 60 photos, his perseverance paid off handsomely. The most well-known of them, dubbed the Pale Blue Dot, was captured at an astounding 3.8 billion kilometers away and depicted Earth as a small and insignificant blue dot in the expanse of space. The Voyager missions are still sharing knowledge from space decades later. Even after 40 years, these spacecraft continue to return useful information from far beyond space. It's interesting to note that the Voyager probes use an outdated 8-track cassette technology, which was widely used in the 1970s. This demonstrates the mission designers' astute preparation since they selected robust and dependable technology. These tapes include vital scientific information on planets, moons, and the interstellar medium, providing answers to some of the deepest mysteries of the cosmos in contrast to ordinary cassettes that played music. What's even more astounding is how these spacecraft managed to carry out their job despite enduring harsh circumstances, including dramatic temperature changes, space radiation, and the utter nothingness of space. It's similar to sending your grandparents on an Antarctic adventure and witnessing their success and survival. The Voyager mission's use of gravity assist maneuvers, which successfully slingshot both Voyager 1 and Voyager 2 far into the solar system, allowed them to continue their arduous voyage through space. This is when gravitational slingshots, or gravity assists, come into play. It can be compared to a cosmic dance. These spacecraft interact with some of the larger planets in our solar system rather than relying only on their own power. Through the utilization of these massive planets' powerful gravitational pull, the spacecraft is able to propel itself farther into space. They may travel farther than they normally could and conserve fuel by using this strategy. Imagine the giant planet Jupiter, with its tremendous gravitational pull, being approached by the Voyager 1 probe. Voyager 1 was carefully piloted by the talented scientists at NASA's Jet Propulsion Laboratory to pass Jupiter at precisely the correct angle and velocity. Jupiter's gravitational pull on Voyager 1 caused it to accelerate dramatically as it approached, much like a turbo boost in space. Here's where it gets challenging, though. This move calls for extreme accuracy. Voyager may have first drifted off course and perhaps ended up in tragedy if the estimates were incorrect. Fortunately, the NASA crew carried it out flawlessly, and these planetary encounters were a great success. It is rather amazing how precise these procedures need to be. The talented group of scientists and engineers accomplished this on several occasions throughout several missions, not just one. Both Voyager 1 and Voyager 2 were able to set out on amazing solar system trips because of these gravitational aids. For instance, Voyager 2 was able to reach Uranus and Neptune thanks to the speed increases from both Jupiter and Saturn. The Grand Tour, which would not have been feasible without these gravity assists, became a reality. Because of the well-thought-out gravity aids, the Voyager missions were a great success, with Voyager 1 even making it to interstellar space and Voyager 2 following quickly behind. Although the concept of gravity assists is straightforward, its implementation is far from easy. Voyager 2's Grand Tour necessitated extraordinary precision. Any inaccuracy in the timing or angle of these enhancements could have jeopardized the mission. However, the crew had to overcome other obstacles as well. During these maneuvers, they also had to ensure they collected as much scientific data as possible. Astronomers and physicists were able to explore more of space since they gained extensive knowledge on how gravity helps with their work. Over time, they went on to develop the Deep Space Network as a result of this. What do you think? Could we employ gravity assists to go to places outside of our solar system in the hopes of finding extraterrestrial life? Like, comment with your thoughts, and don't forget to subscribe for more.